Hi everyone. In this video we're going to talk about collection and analysis of rate data. So the whole purpose of this chapter is related to the Fogler algorithm in this step, in the rate law. So far in all the problems that you've been doing, the rate law was given in the problem statement, and you were told things like the rate law is first order in A, or the rate law is second order in A, and then from that statement you could write the rate law in this way. Now, while those problems are already telling you what the rate law is and how the rate varies as a function of the concentration of the components, in reality, how do we know that? Well, that's something that's determined experimentally. So what we're seeing in this chapter is how, using experimental data, can we come up with the expression that we would use in the rate law. So the learning objective, there's just one learning objective here, is to know how to analyze experimental data to determine the rate law and rate law parameters using graphical and numerical techniques. So the objective of the procedures that we will use here is to obtain the rate equation. The method is by analyzing experimental data that are taken at the smaller scale, free from transport limitations. In other words, there is no diffusional limitations in the system. Everything that's happening, the slowest step is the reaction step. And finally, the procedure is going to be reversing the steps that we've taken in the Fogler algorithm, basically, for designing a reactor. So let's jump right into the notes. So experimental units. So what are these units that we're using to determine the experimental rate data? So there are two types of reactors that we're going to look at for these experiments. On one hand, we're going to use batch reactors, which we will use for homogeneous reactions. In other words, there's only one phase in the system. Usually that is a liquid phase or a gas phase. And for heterogeneous reactions, we will use flow reactors. And we will see an example with a packed bed reactor. So flow reactors are used for heterogeneous reactions. In other words, in these types of systems, there are two phases present. One of them is a solid phase. Usually that is a catalyst. And the other phase is either a liquid or a gas phase, where the reactants are. So in a heterogeneous reaction, your reactant molecules are in one of these fluid phases, and they land and adsorb on the solid catalyst, and the reaction happens at that solid gas interface. Once the reaction has happened and your products are formed, the products then desorb from the surface of the solid and go into the liquid or the gas phase. But always consider that one of the phases is solid and the other phase is either gas or liquid. Okay, so that's all we need to know about our experimental units, where we're measuring these quantities that we're going to use to determine the rate law. So now let's see what the methods are for data analysis. So there are two types of methods that we're going to look at, which are differential and integral methods. in the differential method, the flowchart for information is going to be that you first take concentration versus time data experimentally in your reactor. And then you take that data, the experimental data, and you differentiate numerically. And once you've differentiated the experimental data numerically, you then fit the data to a rate expression. Okay? So these are the three main steps. We will do examples a bit later on in the notes, but for now, just remember that there are these two, and we'll come back to these also later. Now, on the other hand, integral methods are a bit different. For an integral method, you start with a rate expression. So you take the rate expression, you guess it, you guess an expression, you guess a model, and then you integrate it analytically. And once you've integrated it, you fit that expression to the rate data that you've obtained experimentally. Okay? So in one case, for differential methods, you start with experimental data, you differentiate those data points, and then you fit them to a rate expression. Whereas in an integral method, you guess a rate expression, you integrate it analytically, and you fit that integration to the experimental data. Okay, so let's look at the first case for differential methods. Now, we're going to use the differential methods in batch reactors. So of these two reactors that I mentioned up here, we're looking at this situation of a homogeneous reaction happening in a batch reactor. And we're now going to follow these steps. So for this system, things to keep in mind are that we start with the mole balance or design equation of the reactor in the differential form. And we're also going to consider that in this batch reactor, we have a batch reactor where temperature and volume are constant. We're parting from this premise, okay? So, our first step is going to be to use the mole balance equation or the design equation for a batch reactor, which is dNA dt is equal to RA times V. Remember, this is the differential form of the equation. We're not using the integrated form, but the differential form. And from here, because we said that the volume is constant, we can take this term, this volume term, to this side divided by Na, and now the expression would become dCA dt is equal to RA. Now, we're going to combine this mole balance equation with the rate law. dCA dt is equal to the rate law. Now, we do not know what the rate law is, but we know that it's going to be the power law model. So it's going to be minus a constant times the concentration of A to the power of a number that I don't know and that I'm going to call alpha. I'm assuming here that A is my only reactant in the system. So with this now, my experimental data would come from here, the dCA dt, which I would be measuring Ca experimentally for different times in the batch reactor. I would determine what the derivative of Ca with respect to time is from that experimental data, and that would make it equal to this. I don't know what K is, I don't know what alpha is. But because I have these data points, then I can just take the natural logarithm on both sides of this equation, and in that way I'm linearizing the equation. And then I can plot natural log of negative dCA dt versus the natural log of Ca, which will be a line, and from there I can find the slope of the line, which is alpha, which is the order of reaction, and from the intercept I can find natural log of K, and from there solve for K to find alpha and K. Okay, so now I told you that dCA dt comes from experimental data. So how do we find that value? So let's first look at how we do this graphically. So to find alpha, we would represent natural log of Ca on the x-axis, natural log of minus dCA dt on the y-axis, and from our experimental data we would have some points, and by doing linear regression we would find the slope of this line, which would be equal to alpha. This would be the slope for natural log of Ca on the x-axis, natural log of minus dCA dt on the y-axis. And to find K, once we have determined alpha in the previous step, all we would need to do is now just pick a point on the line, any point on the line, and then solve for the value of K accordingly. So basically we would pick a point, we'd know what the natural log of Ca would be for that point, that would be the x value, its corresponding y value, and we would solve for natural log of K and then K. So K would be equal to minus dCA dt for a point 1 divided by Ca to the power of alpha for that point. In other words, graphically, I'd pick for Ca1, I'd pick this point, which would be natural log of that Ca1. I'd come across, come over, and find natural log of minus dCA 1 dt. And these two values for that Ca1, I already have the alpha that I've determined from the slope. I'd plug that in here and take this value, find the minus dCA. I have the natural log from the graph. I'd from there calculate minus dCA dCt for that point, put in that number here, and solve for k. Or you could also find k just from finding the intercept of this line with the y-axis. Okay? Now, so this would all be if you already have the experimental data for dCA dt. But experimentally, what we are measuring in the reactor, in the batch reactor, is how concentration varies with time. So how are we going to, from these experimental points, determine the derivative with respect to time of the concentration? So there are several ways of doing this. There's a graphical method, there's a numerical method, and I would like you to learn both methods. And then there's a polynomial method that we're not gonna do in class, but that you can use any kind of software to use that method. So let's start with the graphical method using equal area differentiation. So for the graphical method, you're going to start with your data points, which are for different times. What is the concentration in the batch reactor? Next, what you want to do is from there, calculate negative delta Ca divided by delta T at intermediate times. So for this case, my negative, I create a new column, negative delta Ca delta T, and for my first delta T, which would be from 0 to 1.25, let's say it's minutes. For that delta T, I calculate the delta C. So my answer here would be 1.9. So 10 minus 7.63 divided by 1.25 minus 0, delta would be 7.63 minus 10 divided by 1.25 minus 0, and I would have 1.9 here. My next one, for this next interval of time, the value would be 1.1, and this next one here, the value would be 0.6. Next, what you want to do is you want to plot these delta Ca, delta T points. These, in this example, we just have 3 points in the form of a histogram. So you would have an x-axis with time, and your y-axis would be negative delta Ca delta T. And for your first interval, for delta T of 1.25, you'd come here, you'd find 1.25, and then your histogram would have this base, and the height would be 1.9. So that would be somewhere around here. For the next delta, or sorry, for the next time, so we went from 0 to 1.25, your next time is 2.25, which is going to be around here. And for this time of 2.25, the delta Ca delta T that you're obtaining is 1.1. So you'd go up to around 1.1, and you draw the histogram. Your next time is 3.25, and the delta Ca delta T from 2.25 to 3.25, 2.25 to 3.25 is 0.6, which would be around here. Okay? So that's how you determine your, or represent the histogram. Now, next what you want to do is you want to visually find intermediate points on your rectangles here, where if you draw a curve through those points, the area on each side of that curve is going to be the same. In other words, I want to draw a line where if I go from here to here, this area is the same as this area. Okay? And then you continue and you'd go and find one where this area is the same as this area. And from here, this area is equal to this area. All right? Now, once you've determined that point, that line, then from that line, you can read the negative dCA dt points on the obtained red curve. Now, I didn't draw a red curve, I drew a blue curve, but I'm going to represent those dCA dt points in red. So the first one would be over here, the second one would be over here, third one here, and my final one would be over here. So those red arrows. So if we read the values of the red arrows, so this is around 2.5. This one over here, if you come across and read it, it's almost around 1.5. This one would be around 0.75. And this one here would be around 0.45. Okay, so 2.5, 1.5, 0.75, and 0.45. So these are my negative dCA dt values, which I can now create a column here and represent that, or those points. Minus dCA dt for this experiment would be 2.5, 1.5, 0.75, 0.45. So these are the data points that I would then create another column to calculate the natural log of these numbers, which I would then represent in this graph. For the natural log of these CAs, which I would represent on the x-axis in this graph. Okay, so that's the graphical way of doing this. Now, how about the numerical method? So the numerical method, or numerical differentiation of the experimental data, you can do using numerical differentiation formulas, only valid when your x values, in this case time, are equally spaced. So if I'm at regular intervals of time, same intervals of time, measuring the concentrations in the batch reactor, then I can use, for example, the 3-point differentiation formula to calculate dCA dt. So here are the formulas. You don't need to memorize this. This comes from numerical methods. You might have already studied this or not, but this is something that you can put into your equation sheet, or it would be provided to you on an exam setting to calculate the dCA dt points for all these different experimental data points. So what you'll notice is that for the first and the last point, these are the two equations that you would use in terms of the concentrations and the delta T. But for all intermediate points, in this case for T1, T2, and T3, the dCA dt values you'd calculate using this formula. We will do an example later on where we will apply these formulas, and that way you'll get to practice and see how it feels. So that's it with the differential method, the graphical method and the numerical method to use the differential method. So again, what we're doing is we're taking the CA, the concentration time, we're taking the concentration time data. In this case, we're taking the concentration time. We are differentiating numerically. That's what we're doing to find dCA dt. And then we are fitting it to a rate expression. In other words, we're taking a rate expression minus kCa to the power of alpha, and we're fitting those experimental points to this expression, which when we linearize, when we can calculate the value of alpha and k. And once we have alpha and k, we've got the rate law. R would be negative whatever value we find for k times Ca to the power of whatever value we determine for alpha. All right, now what are the steps that we would follow in the integral method? So in the integral method, what we're doing is we're going to follow this procedure. So note that this method is actually going to be faster than the differential method, only for rate laws that have a low order, okay, 0, first or second order. Once we get to higher orders, it's going to be a bit more complicated. So another point this is a point that was made in the book, that the integral method is used more in cases where the reaction order is known and we want to evaluate the specific reaction rate constant K. Yeah, that is a case, but you can also use it when you don't know what the reaction order is. You would just guess the reaction order, follow the steps, and see if it aligns or not. And that's what we're going to do here. So we'd start with the mole balance equation for the batch reactor. Remember, we have constant temperature and constant volume, so the mole balance equation in the batch reactor would be dCA dt is equal to RA. And now we would combine this with the rate law, same as we did earlier. dCA dt would be equal to minus K times Ca to the power of alpha. Now what we do is we guess a value for alpha, and we integrate this expression to find an expression for Ca as a function of time. So we guess the alpha value, and then we integrate. We linearize the expression and represent it graphically, and then we contrast the data points, that graph, with the data points that we obtain experimentally. Now, if the order that you guessed is correct, then the plot from your linearized expression and your experimental data will be the same. Or when you plot the experimental data, you'll get them all fall on a line. If not, then the guess was not correct. You'd have to guess another number. So let's see an example, or several examples here. So let's assume that the reaction is 0 order. So if our first guess is the reaction is 0 order, then dCA dt would be equal to minus K, because it would be minus K times Ca to the power of alpha, but if alpha is 0, Ca to the power of 0 would be 1, so dCA dt would be equal to negative K. From here, what we said that we would do is integrate to obtain an expression of Ca as a function of time. So we're going to separate variables and integrate. So dCA would be equal to minus K times dt, which I would integrate from Ca naught to Ca, and for time from 0 to t. So once you do this integration, you're basically going to have CA minus CA naught is equal to minus KT. So the expression of CA as a function of time would be CA naught, CA equal to CA naught minus KT. So this is the equation of a line where this is my y value and this time is my x value. So what I would plot is time versus CA, and I should get a line. So I would plot my experimental points for time versus the concentration. So if you plot the experimental and they fall on a line, if you get a good linear regression, then your guess was right, because your experimental data are showing you that this relation is linear, which is what you obtained when you started with a zero order. If experimentally, and by the way, the equation of this line would be CA equal to CA naught minus KT. This is the same as saying y is equal to A plus B times X, where B in this case would be minus K. Okay? Okay. Now, if you plot your experimental points and your experimental concentration as a function of time, and it does something like this, well, then it doesn't fall on a line, and therefore that guess of zero order is not valid. You would know that that is not the order of your reaction, so you'd have to guess another number. Or if it did something like this, same thing. It's not falling on a line with this slope of k, or your k value here would not be, it would just be, it would just be a constant number. So CA would be constant, which means that you would not have a slope. Your slope would be 0, which is doesn't make sense. Okay, so so let's assume that your data, your experimental data, do not fall on a line with a slope of minus k. So then you'd have to guess that the order is not 0, it has to be something else. What if it were first order? So same thing, we'd start with a first order reaction, dCA dt would be equal to minus k times CA. And from here, if I integrate so that I can separate variables and integrate so that I can find an expression of CA as a function of time. So I'd separate variables. In this case, I'd have dCA over CA would be equal to minus k times dt. And now I would integrate from 0 to t, from CA naught to CA. And this would, this integral would be natural log of CA naught over CA is equal to KT. I mean, if I look at it on this side, it would be natural log of CA over CA naught equal to minus KT. But if I take that minus and inverse it here, so this would be now positive, and here I'd have natural log of CA naught over CA. Okay, so this is also the equation of a line where this would be my y value, and this would be my x value, and the slope would be k. So what I want to plot here with my experimental data is on the x-axis time, on the y-axis natural log of CA naught over CA. I would know what the value of CA naught is, and CA for each time, I'd use that value of CA here for the natural log. And then I'd represent my experimental data. So if the experimental data does something like this, if these are my points which fall on a line where the equation of the line would be natural log of CA naught over CA equal to KT, then I'm good. That's my guess. But if these points do something like this, they don't follow the equation of a line, they do something like this, exponential or parabolic, then that means that my reaction is not first order. Because for the reaction to be first order, when I represent the experimental points T versus natural log of CA naught over CA, it has to be a straight line. If it's not, the guess is not correct. And then what happens if we guess a reaction second order? So for second order, dCA dt would be equal to minus K CA squared. And if we separate variables and we integrate, in this case we would have dCA over CA squared is equal to minus K dt. And we're integrating from 0 to t and from CA naught to CA. So in this case, integral of dx over x squared. Following the integration rules, this would be minus 1 over CA minus 1 over CA naught is equal to minus KT. And from here, doing algebra, 1 over CA would be equal to 1 over CA naught plus K times T. In this case, this is the equation of a line where y is 1 over CA, T is x, K is the slope, and 1 over CA naught is the intercept. So what we would plot then in the graph is on the x-axis time, on the y-axis 1 over CA. And then again, our experimental points, if they fall on a line, then it means that our guess of second order is correct, and the equation of that line is 1 over CA is equal to 1 over CA naught plus KT. If the experimental data don't fall on a line and do something like this, or do something like this, then that means that our guess was not correct and the reaction is not second order in CA. Okay, so now we're going to move on to doing an example where we're going to follow all these steps, both for the differential method and the integral method, to determine the rate law. Okay, so determining the rate law using differential methods in batch reactors. The following reaction, A plus B gives C plus D, is analyzed using the differential method. And the concentration time data, the concentration versus time data obtained experimentally in the batch reactor are shown in the following table. So you've got your time, which is at regular intervals of 50 minutes, and the concentration of A to the power of 10 to the 3 is equal to these numbers. Okay, so in reality, the concentration of A at time 0 would be 50, or 50 would be the result of taking the concentration and multiplying it by 1,000. So we take this number, if we divide it by 1,000, that's what the concentration of A is going to be in moles per cubic decimeter. So it would be 0.05 moles per cubic decimeter. And at time 0, Ca is 0.05 moles, and the initial concentration of B is 0.5 moles. So this concentration of B is much higher than the concentration of A. It's an order of magnitude higher. And this is important because it's going to help us make an approximation which will facilitate our calculations. And now, in part A of the problem, what we're asked is to determine the reaction order with respect to A, using both the graphical method and the finite differences method to determine dCA dt. The finite differences method is the graphical method that we used over here to determine dCA dt. Okay? So, okay. And then in the second part of the reactor, of the problem, it asks us, in a separate set of experiments, the reaction order with respect to B was found to be first order. Determine the specific reaction rate constant. Okay, so let's start with part A. So the first step we need to follow is write the general form of the rate law and simplify in terms of the measured variable. In this case, the measured variable is Ca. So negative Ra, I know, is going to be K times Ca to the power of alpha. I don't know what that value of alpha is, but I also have my reactant B, and that could be influencing in the rate law. So I'm going to write Cb to the power of beta. I do not know what beta is. However, what the problem is telling you is that Cb naught, which is 0.5 moles, is much larger than Ca naught, which is 0.05 molar. So because this is so much bigger, what I can do is I can consider that negative Ra is K times Cb naught to the power of beta times Ca to the power of alpha. If Cb naught is much larger than Ca naught, it means that however much A reacts, that amount of A will react with the same amount of B. It's a 1-to-1. But because B is so much higher, it's the concentration of B, it will decrease because it's reacting, but it will decrease so little that for all intents and purposes, I can consider that Cb is approximately equal to Cb naught, that's not changing so much. And therefore, I can just write the concentration of Cb as Cb naught. And since Cb naught is a constant and K is also a constant, I can consider all of this as a constant. And I'm going to call all of that K prime. Okay? So now my negative Ra is equal to a constant K prime times Ca to the power of alpha. And now I can follow all the same steps that I followed in the notes. So our next step is to combine the mole balance with the rate law. So negative dCA dt is equal to Ra, which is equal to K prime times Ca to the power of alpha. My next step is to linearize. Natural log of dCA, negative dCA dt is equal to natural log of K prime plus alpha times natural log of Ca. All right, fine. Now I want to be able to represent natural log of dCA dt obtained from the experimental data versus natural log of Ca from the experimental data to find the slope and the intercept to calculate alpha and K prime. So where can I get dCA dt? I'd have to use that graphical method to determine that. So, or use the finite differences method. So let's write in our data. The data given for time, for 0 minutes, 50 minutes, 100, 150, 200, 250, and 300 minutes. The value of CA times 10 to the 3 is 50, 38, 30.6, 25.6, 22.2, 19.5, and 17.4. I've just copied these from the original table that is given in the problem statement from this table. Okay? Now the next column that I want to create is the delta CA minus delta CA delta T times 10 to the power of 4 moles per cubic decimeter per minute. And to calculate that, I'm going to take this interval of time from 0 to 50 and my delta CA, which would be the difference between 50 and 38. And when I do this, I'm going to get 2.4. So this difference divided by this difference. Over here, for the next interval from 50 to 100, the change is 38 to 30.6. And when you do the numbers, you'll get 1.48. The next interval, 1.0, 0.68, 0.54, 0.42. Okay, so now that we have the delta CA, delta T, using the finite differences method, we're going to determine the values of dCA or negative dCA dt times 10 to the 4 in moles per cubic decimeter per minute. The units don't change, same as the delta CA, delta T. So how do we do that? So we'll have to go and represent first these delta CA, delta T's in the form of a histogram versus time. So I've gone ahead and already done that, but basically what I'm doing is I'm going from 0 to 50. From 0 to 50, my delta CA, delta T is 2.4. So from 0 to 50, I go all the way up to 2.4 and draw that bar, okay? From 50 to 100, I have 1.48. So I draw the bar from 50 to 100 all the way to 1.48, and so on and so forth. All right. Now what I want to do, and I've already kind of drawn the curve, but I'll do it again here because it takes several attempts to do it properly. I want to draw the curve which is going to give me the same area on both sides of the points that I determine on each one of these bars. Okay, so more or less the ones that I've determined, and this might take, as I said, you're not going to get it on the first attempt. You want to use a pencil or something and sketch different ones, different curves until you get the one that satisfies you in terms of areas. So I'm going to use a different color here. This is the one that I'm going to go with. Oh, okay. Already I'm not getting a good curve here. More or less. Okay. Now, from here, I want to find the DCA DT points, which are going to be the intersections of this curve with the vertical part of these bars. Okay, so the first one is over here. It's a 3. The next one is over here. It's around 1.86. The next one over here, around 1.2. Here I have around 0.8. This one around 0.6. 0.47, and here 0.38, more or less. Your numbers might be a bit different from mine. That doesn't matter. The important thing is to at least attempt to draw this curve where these areas are similar or the same. Okay? More or less. Okay, so these are the points. The red numbers are the points that I've determined, which I'm going to now put into my table for DCA DT. So DCA DT for time 0, it's the 3. For time 50, it's 1.82. For time 100, it's 1.2, and so on and so forth. So plugging in those numbers in the table, I have 3, 1.86, 1.2, 0.8, 0.6, 0.47, and 0.38. All right, now I can represent I can try to now use these data points to represent natural log. So represent natural log of CA. Remember, if this is the equation of a line, this would be Y, this would be A, alpha would be the slope, and natural log of CA would be X. So I'd represent natural log of CA versus natural log of minus DCA dt. And when you do that, you can do that in Excel. So natural log of these points versus natural log of these points. And you'll get a line that has a slope of approximately 1.99. You might get a line that it gives you a slope of 1.86. It's still close to 2, so we're going to just approximate it to 2. All right? Now, so that's the slope. What's the value of K prime? So for alpha equal to 2, K prime would be negative DCA dt divided by CA to the power of 2. Okay, what I'm doing here is I'm just taking my equation, negative DCA dt is equal to K prime times CA to the power of alpha, but I've determined alpha as 2, so I'm solving for K from here. Negative DCA dt over CA, and I'm just going to pick any point, any of my experimental points, and find the corresponding DCA dt for a particular CA. So let's say that I pick the point at 100 minutes, 30.6. So CA square is going to be 30.6 times 10 to the power of minus 3, because remember, this is the result of taking CA and multiplying it by 1,000. So the actual value of CA would be 30.6 divided by 1,000 square. And in the numerator, I'd have the corresponding value of negative dCA dt, which is 1.2 times 10 to the negative 4. And this is going to give me a value for K prime of 0.128 with units of cubic decimeters per mole per minute. And one more important thing to mention is that in my x-axis, I'm representing time, and on the y-axis, I'm representing negative dCA dt times 10 to the 4, and also negative delta CA delta t times 10 to the power of 4. Okay. Okay, so we found alpha and we found K. We're done. We're done with doing this by using the graphical method. How about the finite difference method? So this would be the numerical method. Let me focus. Okay, so the numerical method, we'd have to apply that equation that I showed you earlier. So that would be the 3-point differentiation. So 3-point differentiation, these are the equations that we need to use. These two would be for the first and last points, and for all intermediate points, we'd use this equation. So let's start with the first point. For time for time 0, that's my first point. For time 0, dCA dt for t equal to 0, the formula that I'd have to use is minus 3 times CA naught plus 4 times CA1 minus CA2 divided by 2 times delta t. So if we look in our table, CA naught for time 0, CA naught is 50. So I'd have minus 3 times 50 plus 4 times CA1, which would be 38, minus CA2 for time CA naught 1 and 2, CA2 would be 30.6, and of course I'd have to remember to multiply all of these by 10 to the negative 3, divided by 2 times delta t, where delta t is 50 minutes. So plugging in those numbers, I'd have minus 3 times 50 plus 4 times 38 minus CA2 is 30.6, and I'm multiplying all of these concentrations times 10 to the negative 3 divided by 2 times delta t, which is 50 minutes. Okay, and then plugging in the numbers in your calculator, what you'll obtain is minus 2.8 6 times 10 to the negative 4 moles per cubic decimeter per minute. Okay, now we need to do this for all of the times that we have. The next time is for the time 50. Your next data point is at time 50. So we're going to use the expression for intermediate points, dCA dt at t equal to t1, which is 50 minutes. The equation, going back to the notes, the equation for intermediate points is, if I'm at point time 1, I'm going to take the concentration at the next time minus the concentration at the time before. So in this case, it would be, since I'm in point 1, I take Ca2 minus Ca0 divided by 2 times delta T. So 2 times delta T. So in my table, Ca2, where's my table? So in the table, Ca2, this is Ca0, 1, 2 is 30.6, Ca0 is 50, and delta T is 50. So 30.6 minus 50, both of them times 10 to the negative 3 moles per cubic decimeter divided by 2 times 50. That's 100. So the number that you're going to get here is minus 1.94 times 10 to the negative 4 moles per cubic decimeter per minute. For time 100, still an intermediate point, so I'm going to use the same equation, but now for different points. So at time equal to time 2, which is 100 minutes, I'd have, since my point is 2, here I'll have the concentration of 3 minus the concentration of the point. So it's the concentration of the point after point 2 minus the concentration of the point before point 2. That's Ca1 divided by 2 delta T. And that is going to be 25.6 minus 38. You can get that from the table, times 10 to the negative 3 divided by 2 times 50, which is 100. And this value will be minus 1.24 times 10 to the power of minus 4 in moles per cubic decimeter per minute. And you do this for all the points up to 250. So for 150 minutes, following all these same steps that I did here, you should get minus 0.84 times 10 to the minus 4, same units, moles per cubic decimeter per minute. For time 200 minutes, following the same steps, you'll get minus 0.61 times 10 to the negative 4, same units. For time 250, you're going to get minus 0.48 times 10 to the negative 4. And then for time 300, we cannot use the same equation as we did for all the intermediate points because it's the last point. So if you look back in your notes, the equation for the last point is, here we did it for this example, so it's going to be the last 3 points. So the concentration 2 points before the last point minus 4 times the concentration before the last point plus 3 times the concentration of the last point divided by 2 delta T. In this case, for T300, dCA dt at T equal to T6, we'd have 2 points before it's the concentration at point 4 minus 4 times the concentration of the point right before that point, which is Ca5, plus 3 times the concentration of the last point, divided by 2 times delta T. So plugging in the numbers from your table, you're going to have 22.2 minus 4 times 19.5 plus 3 times 17.4. All of this multiplied by 10 to the negative 3 divided by 100. And this will be minus 0.36 times 10 to the negative 4 moles per cubic decimeter per minute. And then with these points, you would plot the natural log of minus dCA dt for the values of dCA dt that you have obtained here, all these points, this one, this one, this one, and all of these. You'd find their natural log and plot versus the natural log of Ca. And from there, you should get a slope of 1.9959 with the numbers that I have here, which again is very similar to 2. And from here, and from the intercept of that line with the y-axis, you're going to get a K prime of 0.123 cubic decimeters per mole minute. So remember, the intercept of the line with the y-axis is going to be natural log of K prime. And then from there, you calculate K prime as 0.123. So very similar values to what we obtained graphically, I believe. Similar values. Yeah, so graphically for time 0, we got a 3 here. Here we're getting negative 2.86. So note that this is dCA dt, and here we're representing negative dCA dt. That's why this has a negative sign, and this one is positive, okay? Once you take the negative dCA dt's, all of these are going to be positive numbers that you'd have in the natural log here. So we had 3. The next one was 1.86. Here we get 1.94. Let me bring in the table. That's going to be easier to compare. 1.94, 1.24, 1.2, 0.84. Here we have 0.8, 0.61, 0.6, 0.48, 0.47, and our last point was 0.36, and graphically we got 0.38. So they're close, and once you represent, like, your slopes are going to be very same when you linearize the equation and represent the data points. So you're going to get very, very similar numbers. For K prime, graphically, when we use the graphical method, we're getting a K prime of 0.128. With this numerical method, we're getting 0.123. So that's actually decent proximity between the two methods, the answers we get with the two methods. So that's nice. Okay, so that's that example. Let's take a pause and look into the second example where we're going to use the integral method. Okay, I just realized we did not finish part B of the problem. So let's do part B first, and then we'll do the next example. So part B of the problem is telling us, in a separate set of experiments, the reaction order with respect to B was found to be first order. Determine the specific reaction rate constant. So it's asking us to find k. What we obtained earlier was k prime. And we cannot really calculate k until we know what the order in B is. And that's what part B is telling us. It's telling us that this beta value is 1. So once we have that, then we can solve for k. So beta is 1. If beta is 1, and we're assuming still that because CB naught is so much higher than CA naught, we're assuming that CB over time does not change very much and it's approximately equal to CB naught. So from there, we can then say K prime is equal to K times CB naught. And solving for K is K prime divided by CB naught. So we obtained K prime earlier in part A. Let's just go with this one, with how we did with the numerical method, 0.123 cubic decimeters per mole per minute divided by CB naught to the power of beta, which is 1. So CB naught is 0.5 moles per cubic decimeter. So the value of K is 0.123 divided by 0.5. I'm going to write it here. K is going to be equal to 0.246. And the units are going to be cubic decimeters per mole squared times 1/minutes. Therefore, the rate law is minus RA is equal to K 0.246 times CA to the power of 2 times, from part B, the other experiment that told us that it's first order in B. So this is the rate law, the final rate law for this problem. Okay? Okay, now we can move on to the next experiment. Take a pause if you need, pause the video, and then we can continue. You can continue. So here we're going to be applying the integral method. So it says, for the same reaction as in the previous example, use the integral method to confirm that the reaction is second order in A. So we already know that it's second order because we found it earlier, but now we want to confirm it using the integral method. So the integral method, remember, was you start with your design equation and you take a guess at what the rate law is. In this case, we're told it's second order, so K prime times CA to the power of 2. And now we're going to separate variables and integrate this expression. So integrating, knowing that CA is equal to CA naught at a time 0, separating variables, integrating, we get that 1 over CA is equal to 1 over CA naught plus K prime times T. So you would now plot 1 over CA, the experimental CA, versus the experimental time. And what you'll observe when you do it, you can do this on Excel, you will observe that your data points are going to fall on one line. Again, here I'm representing time versus 1 over CA. They'll fall on a line when you do linear regression, and the equation of your line is going to be 0.1248 x plus 20.118 with a regression R square of 0.9999. So your experimental points do fall on a line. Therefore, you're confirming that way that it is second order because you started with the second order equation and you integrated and then you plotted and they fall on a line. So as you can see, going back to the beginning, for the differential method, which was the first example we looked at, we started with the concentration versus time data. We differentiated those experimental data points and calculated dCA dt. And then we fit those to the rate expression. In other words, we linearized the expression and then we did a linear regression to find the slope, which was alpha, and the y-intercept, which helped us determine the value of k. In the integral method, we start with a guess. And in this case, we didn't have to guess a lot because it already told us that it's second order. But we take a guess for what the rate expression is. We integrate with respect to the guess that we took, and then we see how it fits with the experimental data. So two very different methods following a different path, but at the end serving for the same purpose, which is to determine the rate law for a reaction. And by the way, the K prime that you obtain over here, 0.1248, is very similar to the K prime that you found in the previous differential method, which was around 0.123. All right. Now, we've talked all this time about batch reactors for homogeneous reactions. But now, what do we do when we have a heterogeneous reaction? That's going to be what we're going to talk about next. What you'll see in your notes on page 5 is this part here on nonlinear regression. There's nothing for you to copy here. I'm not going to ask you to do this in class or for the exam, but it's just here for you to have for your general knowledge. Nonlinear regression is going to be a method that you can use. You've maybe seen it in numerical methods. You can also use Python to solve for this, but basically what nonlinear regression does is that with all the parameters that you give to the system, you can simultaneously solve for the order and for the order of reaction and for the K value. So basically you would input your experimental data and you would ask it to simultaneously solve for the orders of reaction and the K value. And it would automatically do all of these calculations for you based on the steps for nonlinear regression. And I'm not gonna. I think you can read this yourself and have it for your general knowledge. Okay, so heterogeneous reactions. So in a heterogeneous reaction, the type of reactor that we use is different. We don't use batch reactors anymore, but we still need to use these packed bed reactors or flow reactors in order to find the experimental data that will then allow us to find the order of the reaction and the rate constant. So let's talk a bit about the type of reactor that we're going to use. For these reactions, we're going to use what we call a differential reactor. Differential reactors are very small. They are packed bed reactors that are used experimentally to determine the reaction rate as a function of concentration or partial pressure. Note that a lot of times when we have gas phase reactions for the rate law, instead of expressing it in terms of the concentration of the components, we express it in terms of partial pressures because we're in a gas phase. This is the most common type of the catalytic reactor, this differential packed bed reactor, that is used at the lab scale to obtain experimental data. And in fact, in our lab, we do catalysis research, and all the reactors that we have are differential packed bed reactors. We're talking about sizes where the inner diameter of the tube is like 1 centimeter. So they're very small, but there's a reason why we want these reactors to be very small, because we want them to be differential. What does that mean? So we'd have a packed bed reactor. It's got a length delta L. We have a reactant going in at an initial concentration, Ca naught, initial molar flow rate, Fa naught. The reaction happens, and what we have at the exit is whatever A didn't react comes out with a molar flow rate FAE, where E stands for exit. And then we have the molar flow rate of our product, Cp, and the concentration of the product, Fp and Cp. So P stands for product. So what are the criteria for a reactor to be considered differential? Here are 4 points that have to be fulfilled. The reaction happens isothermally. In other words, the temperature is constant throughout the bed. The conversion needs to be very small. We do not want the reaction to happen to a very large extent. We want to keep conversion low. Ca, when the conversion is low, Ca will not change very much. Through the reactor because the conversion is low. And another important point is that the reactant flows uniformly across the bed. We want there to be uniform contact between the reactant molecules and the entire bed. We don't want them to channel through preferential pathways and not be in contact with other parts of the catalyst bed. We want the flow to be very uniform throughout the entire bed. So, under these conditions, what is the design equation going to look like? Well, since the differential reactor is assumed to be gradientless, there is no gradient in temperature, there is no gradient in concentration, Ca is not changing very much, temperature is not changing throughout the bed, it's all the same, everything is gradientless. The design equation will therefore be similar to the CSTR design equation. Even though it's a tubular flow and it's a plug flow, but because it's so small, because there isn't a gradient, the concentration is not varying constantly throughout the bed, then we can treat it as if it were a CSTR. And the steady state mole balance on A is now going to be Fa going in minus Fa coming out plus whatever A is generated inside the reactor. Because it's a packed bed reactor, I'm going to use Ra prime, which is per mass of catalyst, and therefore I'm going to have to multiply it by the mass of catalyst in the reactor. And at steady state, all of this is equal to 0. So from here, I'm missing a minus negative Ra prime. Please correct this in your notes. The negative Ra prime is going to be, just doing algebra from here, Fa naught minus Fae divided by delta W. And in terms of concentration, this would be V naught times CA naught minus V times CAE divided by delta W, where this is the volumetric flow rate going in, this is the volumetric flow rate coming out. And all of this, according to all of this, so this is going to be FA naught times X over delta W. And FA naught times X is the flow rate of the product divided by delta W. Okay, now if the volumetric flow rate doesn't change, if there's no change in volume, then this expression here will just be V naught times CA naught minus CA at the exit divided by delta W, and this is the same as V naught times CP divided by delta W. So experimentally, we can determine the rate, the experimental value of the rate of formation of A by just measuring the concentration of the product at the exit, knowing how much catalyst weight we have in the reactor, and knowing what volumetric flow rate we're feeding to the reactor. Which is very nice, because now experimentally I just need to know what this concentration of the product at the exit is, and from there I can determine the rate for the reaction. Now, since this value is very small, because we're just saying that CA does not change much through the reactor, conversion is small, then we can say that the rate of A is a function of the concentration of A in the catalyst bed. So this B stands for in catalyst bed. And CAB in the catalyst bed is going to be the average of the CA going in and the CA coming out. So the sum of those two divided by 2, which is really very similar to CA naught, which means that by changing the concentration entering the reactor, I can get different rates and express the rate of reaction as a function of the initial concentration of A. Okay? So let's do now an example where we're going to determine the rate law using a differential reactor. That's on the next page. And we're going to apply all of these equations that we derived here. So we have the following reaction happening in a gas phase. We have hydrogen in the gas phase reacting with carbon monoxide in the gas phase to give me methane and water. Determine the rate law for the following reaction. The reaction is carried out in a differential packed bed reactor using 10 grams of a nickel catalyst and a feed with an entering volumetric flow rate of 300 cubic decimeters per minute. So this is V naught. The experimental data measured in the reactor are shown in the table below. So for different initial concentrations of CO and hydrogen, we are determining the concentration or measuring the concentration at the exit. One thing to note here, consider, this should be a part of the problem statement, okay? Consider that the exit volumetric flow rate is equal to V naught. In other words, lowercase v, volumetric flow rate, is constant throughout the reactor. So, to determine the rate law, first what we need to do, let's just go through the steps first and then we'll do them. First, we need to calculate the experimental rates. Calculate experimental rates. Second, we're going to assume that the rate of formation of methane is a function of the concentration of CO and a function of the concentration of hydrogen. So it's a function of the concentration of the two reactants. F and G stand for just functions. The function F of C, G of H. Okay, F of CO, G of hydrogen. And third, find the dependence. How? What is this function? How does the rate vary with the concentration of CO and with the concentration of hydrogen? So find the dependence between R prime and concentration. Okay? Okay, so I have the concentration at the exit. I want to calculate the rate. So let's do the first step. So first, the rate of disappearance of CO prime, we're going to not assume. We know that we're in a packed bed reactor, so we're going to use the rate in terms of R prime. The rate of disappearance of CO is going to be equal to the rate of generation of methane. Why? Because it's a stoichiometry of 1 to 1. Okay? So for that stoichiometry, the rate of reaction is the rate of generation of methane. And as we said earlier, when we're using a differential reactor, we can treat it like a CSTR. And from all the steps that we derived here, we said that the rate of reaction or the rate of disappearance of the reactant is going to be, let's go with this equation. The molar flow rate of the product divided by the weight of the catalyst in the bed. So here, the mole of product would be the molar flow rate of the reactant going in times the conversion divided by delta W, which is F divided by delta W, and the molar flow rate can be expressed as volumetric flow rate, which is constant in this case, times the concentration of methane divided by delta W. Okay, so I know that the volumetric flow rate is 300 cubic decimeters per minute. The concentration changes with each run, so I'm just going to write it as C of methane in moles per cubic decimeter divided by delta W, which is the mass of catalyst, which is 10 grams of nickel. So 10 grams. So for each of these experiments where we're starting with different partial pressures of the reactants, different relative partial pressures, we're going to calculate the rate. So we have the concentration, we can calculate the rate. R CH4 prime, because this is times 10 to the 4, if you actually plug in the numbers, if you take this 1.73 times 10 to the negative 4 in here, multiply by 300, and then divide by 10, the result that you will get is 0.0052, which I can also write as 5.2, and this rate here would be times 10 to the 3 moles per minute per gram of catalyst. I'm writing this times 10 to the 3 so that I don't have very large significant figures here. I don't want to write 0.0052, 0.000, whatever. Let's just keep it this way. And we're multiplying up here. So 5.2. So plugging in for each one of these concentrations in this equation, we're going to obtain these rates here. The next one will be 13.2, 30.0, 4.95, 7.42, and 5.25. So all of these numbers are coming from this equation, okay? And using this concentration over here. Okay, so we've got the rates, we've calculated the experimental rates. Next, we want to determine how the rate varies with the partial pressure of CO and with the partial pressure of hydrogen. So let's find, that's going to be the third step, is find the dependence. So let's go with CO first. The dependence on the partial pressure of CO, of the rate. So now if you go here, you're going to see that as the partial pressure of CO varies in these first 3 experiments, the partial pressure of hydrogen remains constant. Like, we're on purpose, we're keeping it constant. And we're varying the partial pressure of CO at the entrance of the reactor. Okay? So by varying this and maintaining this constant, we're seeing that our rate is changing. So now we want to see, well, how does this rate change when I vary this? Okay? So for runs 1 to 3, pH is constant. That does not change. But the rate does change because the concentration of CO, or the partial pressure of CO, is changing. So I can write RC as K times the partial pressure of CO to the power of alpha. Okay? And now, if I represent the natural log of RCH4 prime, or basically I'm linearizing this, same as we did with the homogeneous reactions, I'd have natural log of K plus alpha times natural log of PCO. So what you want to plot now with your experimental data is the natural log of PCO. Remember, this is the equation of a line where this is y, this is the intercept. So A, B is the slope, and this is your x value. So on the graph, you're representing natural log of the partial pressure of CO versus the natural log of the rate of formation of methane. But you only want to do it for runs 1 to 3, because it's only for runs 1 to 3 that the partial pressure of hydrogen is constant and will be a part of this constant number over here. Okay, so when you represent your points, again, do this on Excel and do a linear regression. Actually, you're only going to have 3 points. Okay, so forgive me, just represent your 3 experimental points for these runs. So for these, the natural log of these 3 points of pressure represent the natural log of the rate. You'll get 3 points, and when you do a linear regression with those 3 points, you're going to get a slope alpha equal to 1.23 and a natural log of k equal to minus 5.259. And from here, solving for k, we'll have 0.0056. So the important point to take here is alpha, that the order of reaction with respect to the partial pressure of carbon monoxide is approximately 1. Okay, but we're not done, right? Because we now need to see how things vary when the partial pressure of hydrogen varies. So now we're going to go and find places where the partial pressure of hydrogen is changing, but the partial pressure of CO is constant, because that way we'll be able to analyze how the rate varies only when the partial pressure of hydrogen varies. Okay. So now we're moving on to dependence on the partial pressure of hydrogen. Now, what we observed earlier was that when hydrogen was constant and partial pressure of CO was varying, as this was increasing, as the partial pressure increased, the rate also increased, which is why we could write the expression as k times this to the power of alpha. Because through this expression, knowing that alpha is going to be a positive number, if this increases, this will increase, always. But now, when we're at a constant PCO and P hydrogen is varying, partial pressure of hydrogen is varying, what we're observing is that when it varies from 0.1 to 0.5, it's increasing, and the rate is increasing. But when I increase by a lot, when I go to much higher pressure, order of magnitude higher, my rate is going down. So I cannot, in this case, write that R is K times pH to the power of alpha, because it is not always increasing the rate does not always increase when this partial pressure is increasing. So we need to separate low pressures from high pressures. So, let's do it this way. At low pressure, when the partial pressure of hydrogen goes up, RCH4 prime goes up. But at high pressure, when the partial pressure of hydrogen goes up, the rate of formation of methane goes down. So this can be represented as RCH4 prime is K times the partial pressure of hydrogen to the power of beta 1 at low partial pressure of hydrogen, and the rate is 1 over pH to the power of beta 2 at high partial pressure of hydrogen. And putting all of this together, RCH4 prime would be approximately a number times P of hydrogen to the power of beta 1 divided by 1 plus a number, we don't know what that is, the proportionality factor we don't know, but it's a number, times the partial pressure of hydrogen to the power of beta 2. So we are writing it this way because when we have high pressures, or no, let's go with low pressure. So when we have a low pressure of hydrogen, this number is going to be smaller than 1. So it would be as if I just had this term were negligible, and the rate would be proportional to the partial pressure to the power of beta, which is what we're saying is happening. When we have high pressure, this term is not negligible anymore, but it might even be higher than 1. So our expression, the 1 would now be negligible. So our expression would be that the rate is proportional to the partial pressure beta 1 minus beta 2. Okay, and that beta 2 would be predominant. Hopefully, we'd have to find what the value of beta 2 is. So combining, so we're going to combine now these equations, combining the equations with dependencies of the partial pressure of CO and the partial pressure of hydrogen, we can represent the rate as A times the partial pressure of CO to the power of alpha, which we obtained earlier was close to 1, times the partial pressure of hydrogen to the power of beta 1, divided by 1 plus B times the partial pressure of hydrogen to the power of beta 2. And here is where, if we do the easiest way to do this is by a nonlinear regression. Which again, I would not ask you to do on an exam, because you'd need a computer or some kind of software or solver to do it. But if you do a nonlinear regression, it basically, with the experimental data points that you have for R, for PCO, and for P hydrogen, you would tell it to do you would tell your program to do a nonlinear regression and simultaneously solve for A, B, beta 1, beta 2, and alpha. And what you're going to get is 0.025 times PCO times P hydrogen to the power of 0.61 divided by 1 plus 2.49 times the partial pressure of hydrogen to the power of 1. So as I was mentioning earlier, this fulfills what I was mentioning about this point here. So if we look at this equation for high values of the partial pressure of hydrogen, this is going to be larger than this, so we can neglect this one, and this would become our equation. And this partial pressure here of hydrogen is 0.61 in the numerator and 1 in the denominator. So overall, we're going to have 0.61 minus 1, we'd have the partial pressure to the power of approximately 4, 0.39 in the denominator. And therefore, if this increases, the rate will decrease. Okay? But again, those are numbers that you'd need to solve with nonlinear regression. I'm just saying, when we do that, we see that this does fulfill the relation that we were seeing between high and low partial pressure and how the rate varies for those variations in the high end and the low end. Okay, so with this, I'm done with this lecture. It's been a long lecture, and in class we will do more examples and answer any questions that you have. Thank you very much, everyone.